Hello there, welcome back to another stats lecture. In this video we're going to talk about measures of dispersion. So this is section 1.8 on measures of dispersion, standard deviation, interquartile range, and index of qualitative variation. When we're describing a data set, we like to be able to describe the shape of the distribution, and we do that by looking at a graph. Okay. We also like to be able to describe the center of the distribution, and we do that with the mean, median, and mode. But another important measure, another important description of a data set is how much spread or how much variety there is in a data set. And that's what we're seeking to quantify in this section. So without further ado, let's head over and talk about measures of dispersion. Okay, so just to kind of get us thinking about this a little bit and thinking about why we might care about how much spread or dispersion there is in the data set, let's consider these two cases, okay? So the dot plots below represent the number of chocolate chips in Subway and Quiznos chocolate chip cookies. In both cases, a sample of 40 cookies was taken. Now, it's interesting to note that the sample mean for each data set is the same, 23.95. But obviously, there's a big difference between these two data sets. I would also describe the shape of these distributions as roughly bell-shaped in both cases, okay? And yet, they're very different data sets, okay? Here we're asked the question, which type of cookie is more consistent with the number of chocolate chips and which one has more variety? So just to make sense of this, right, looking at the Quiznos data, we had 11 cookies that each had 23 chocolate chips in them, 24 cookies that each had 20 chocolate chips in them, and 9 cookies that each had 25 chocolate chips in them. That's remarkably consistent, right? Every cookie had 23, 24, or 25 chocolate chips. Okay? If you compare that to the Subway data, there were 2 cookies with 19 chocolate chips, and there were 7 cookies with 23 chocolate chips, and 1 cookie had 30 chocolate chips. So there's much more variety in terms of the number of chocolate chips you expect to find in a Subway cookie. Much more variety compared to the Quiznos cookies. So which one is more consistent? We would say Quiznos is more consistent. And Subway has more variety. Okay, so our goal in this section is to describe the consistency or the variety numerically. And so one naive attempt to kind of do that is to look at the range. Okay, the range of a set of data values is the difference between the maximum value and the minimum value. So looking at the Subway data, the range, I'm just going to call this range sub S for Subway. The range of the Subway data would be 30 minus 19, the maximum value minus the minimum value. So 30 minus 19, which is 11. Whereas the range of the Quiznos data, I'm going to call that range sub Q, okay, that would only be 25 minus 23. Okay, maximum value minus minimum value, which is only 2. Okay, so at first glance it might seem like, okay, so the range is a good measure of dispersion. It's a good measure of spread. But not so fast, okay, because let's suppose that the Quiznos data happened to have 2 more values in it, and that one of those values was 19 and the other one was 30. So that our Quiznos data now looks like this. Now, I would argue that this data set is still roughly bell-shaped, and the mean hasn't changed very much, and yet I would still argue that this data set is more consistent than that. Okay? The Quiznos data is still more consistent than the Subway data, despite the fact that we have a couple of outliers. Okay? However, when you compute the range of the Quiznos data with those 2 cookies thrown into the mix, well, you would get 30 minus 19, which is 11, okay, which is the same range as the Subway data. So now these 2 data sets have the same range, even though this data set is clearly more consistent than this one is, okay? So obviously the range isn't a super great measure of center, whereas here, if the range is a resistant numerical summary, and we would say no. Remember, resistance is the idea that if you throw in some outliers, your value isn't going to change very much. And here we saw that when we threw in a couple outliers, our range increased from 2 to 11. So the range is not resistant. How good would you say the range is at describing the spread of a data set? Well, not very. Not very good. Because again, these 2 data sets have the same range, even though the Quiznos data is clearly more consistent than the Subway data is. So we need to develop a better measure of spread, a better measure of dispersion. And one really good measure of dispersion is the standard deviation. So the idea behind the standard deviation is that we want to see how far on average each observation is from the mean. That's sort of a loose understanding of the standard deviation. Here are the formulas for computing the standard deviation. We have one formula for computing the population standard deviation, which we denote with a lowercase sigma. Okay, so this is the Greek letter sigma. It's a lowercase sigma. That's also the Greek letter sigma, but it's a capital sigma, and it stands for the sum. But this is our lowercase sigma for the population standard deviation, and then we have a separate formula for the sample standard deviation. Now, you'll notice that these 2 formulas are pretty similar. Okay, we're going to take each observation and subtract it from its mean. All right, observation minus mean. Then we're going to square those values. We're going to add them up, and then we're going to divide by the number of values in the data set. But here we have a slight difference, right? So for the population standard deviation, we divide by n. For the sample standard deviation, we divide by n minus 1. Okay. Now we're going to talk a little bit later on in this section, for those of you who are interested. We'll talk at the end of the section about the derivation of these formulas. Okay. For now, I would just say the reason we divide by n minus 1 for the sample standard deviation rather than just n is because if we divide by n, we will be systematically underestimating the true population proportion, or population standard deviation. And we correct for this by dividing by n minus 1. And there are good mathematical reasons for that we're not going to get into in a ton of detail now. Okay. Let me also just mention that the number that we get before taking the square root is called the variance. So the population variance would be denoted by sigma squared, okay, and the sample variance would be denoted by s squared. And again, these are just the numbers that we get before taking the square root when we're calculating the standard deviation. In Excel, if we wanted to compute a population standard deviation, we would use stdev.p. So we would type in equals stdev.p. And for sample standard deviation, we would do equals stdev.s, right? So p for population, s for sample. And similarly for the variances, right? These are the functions that we would use in Excel. So let's practice a little bit. I'm not going to ask you to do a ton of standard deviations by hand, but let's practice at least once doing a standard deviation by hand so you get a sense for, you know, what it's calculating. And then we'll use Excel to verify our answer. And we'll use Excel in all of our future calculations for the standard deviation. So here we go. We want to compute the standard deviation of this data set. Let's just remind ourselves that the formula for the variance, we're told that this is sample data, by the way. Okay, so we're going to compute the sample standard deviation. The formula for the sample variance, S squared, is the sum of our observations minus our sample mean squared divided by n minus 1. Okay, so that's the formula that we're going to use. In order to use this formula, first we're going to need to calculate the sample mean. So let's do that, right? So the sample mean here is 82 plus 77 plus 90, etc., until we get to the last value of 88. And then we'll divide by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So let's head over to our calculator and see how much that is. So we'll do 82 plus 77 plus 90 plus 71 plus 68. Ooh, I missed the 62. Plus 62 plus 68 plus 74 plus 84 plus 94 plus 88. Okay, that comes out to 790. If we divide that by 10, and of course we get 79. So our sample mean is 79. And now we can use that in our formula for the variance. Okay, so the variance now is going to be our first data value, 82, minus the sample mean, 79, squared, plus the second data value, 77, minus the sample mean, 79, squared, plus the third data value, 90, minus the sample mean, 79, squared, and we're going to continue on this way until we get to the last data value, 88, minus the mean, 79, squared. Okay, and we're going to add all of those up and then divide by n minus 1. Now n was 10, okay, so we would divide by 10 minus 1. Now you could punch all of this into your calculator now. I'm just going to take it maybe a step or two further to make it a little bit easier when I go to punch these things in. But I'll have 82 minus 79, that's 3, squared is 9. Okay, 77 minus 79 is negative 2, and negative 2 squared is a positive 4. Okay, because negative 2 times negative 2 is positive 4. 90 minus 79 is 11, and 11 squared is 121. Again, you could just punch this into your calculator. In fact, I might just cut to the chase and give you my answer. So I'll check back in with you after I've finished calculating this. Okay, so this is what I get after I do all of the subtractions and then squaring of the numbers, and also 10 minus 1 is 9. Now if I throw that into my calculator, then I get 107.1, or 964 over 9. I like to have the exact value because I'm going to take the square root of it now to find the standard deviation. So let's write 964 over 9. Which is approximately 107.1. Okay, so that's the variance. Now the standard deviation, right, that's the variance, S squared, so that means the standard deviation, S, is going to be the square root of 964 over 9. So square root of 964 over 9, that comes out to about 10.3. Okay, and that's how we would calculate a standard deviation. it's a little bit of a nasty process. So we're happy that we have Excel to just do this for us. In Excel, the way this would work is we would just type in standard deviation equals stdev.s, because we want a sample standard deviation of our data. Okay, so let's see if we can get Excel to do this for us. So here's our data set. It's under example 3. Okay, yes, so this is our data set. I'm going to just click into an empty cell and say equals stdev, and I want .s for the sample standard deviation. So I'll arrow down to that and then hit tab. And now I'm just going to select the data, close the parentheses, and say enter. And there we go. Right? About 10.3. Alright, so that's verified in Excel. Okay. Let's do another one in Excel. This one says, use Excel to compute the variance and the standard deviation of the data set if we assume that this data set is population data in part A, and then again if we assume that this is sample data in part B. Okay, so as for the variance, if it's population data, then the symbol we would use is sigma squared, okay, for the population variance. And in Excel we would say this equals var dot p for population. So let's see what that is. So this is example 4. Okay, so for the, let me just label it population, we'll say pop variance. Okay, so the population variance is equals var dot p of this data set. Okay, for the population standard deviation, it would be equals standard deviation dot p of the data set. Okay, so those are my answers to part A. Let's write them down. So we got 10.5, and then for the standard deviation, the symbol for the population standard deviation is sigma. In Excel we would calculate this by going to standard deviation dot p of the data, and we came up with, I forgot it, we came up with 3.2 approximately. Okay, so that's how we would calculate those. Let's do the same calculation, but assuming that we have sample data. So for sample data, the variance would be s squared, and in Excel we would calculate this by going to var.s. Okay, s for sample. And for the standard deviation, it would be s equals standard deviation dot s. Okay, so let's see about how much these are. So the sample variance is going to be equals var dot s of the data set. Okay, so that comes out to 12 exactly. And for the sample standard deviation, let me make this a little wider so we can see those. So for the sample standard deviation, it's going to be equals standard deviation dot s of the data. Okay, so about 3.5-ish. So 12 and 3.5. Okay, so as you're being asked to compute variances and standard deviations, just be aware of whether the data that you're working with is population data or sample data, because that will affect your answer. Now, it may be interesting for you to note that the Subway chocolate chip data, this data, has a standard deviation of 2.6, right? 2.6, while the Quiznos chocolate chip data, that's this data here, has a standard deviation of 1.4. Okay, so it seems like the standard deviation is doing a fairly decent job at describing how spread out the data is, right? Because the smaller standard deviation here indicated that we have less variation, right? The larger the standard deviation, the more spread there is in the data. The smaller the standard deviation, the more bunched up our data is. So, in summary, the standard deviation is a measurement of how spread out the data are. It tells us how far on average the observations are from the mean. And a large standard deviation indicates a lot of spread. A smaller standard deviation indicates more consistency, or less variety, less spread. Okay, so just to give one last example of that idea, suppose that you're a talent scout looking to recruit a soccer player for your team. Player A scores 1 goal per game on average with a standard deviation of 0.5 goals per game, and player B scores 1 goal per game on average with a standard deviation of 0.75 goals per game. Part A asks which player has the better scoring average. And that's something of a trick question because the answer is neither of them, or in other words, they have the same scoring average, right? Neither. Right? They both score 1 goal per game on average. Okay. But now part B asks, which player is a more consistent goal scorer? And the answer there would be player A, because player A has a smaller standard deviation, so they're more consistent. There's less variety, okay, with player A, less variation. So therefore more consistency. So we say player A, because he or she, I guess, has a smaller standard deviation. Now part C asks, whom would you rather recruit and why? I don't think there's necessarily a right or wrong answer here. You might say player A because player A is more consistent. Then again, you might say player B because player B, there's more variety, and so maybe player B is less easy to predict. Or maybe you could say on a really good day, player B is going to score more points because, you know, there's more variety in his performance. So you could argue either way. Personally, I would rather go with player A because he's a more consistent scorer. All right, so that is the idea behind standard deviation. Let's talk about the interquartile range. This is something that we've actually brought up before. Okay, so we talked about the interquartile range when we were looking at box plots and identifying outliers. Okay, we're going to bring it up here as a measure of dispersion, because you may have noticed that the formula for the standard deviation uses the mean, which is not good for skewed data. And consequently, the standard deviation is not going to be good for skewed data. Okay? On the other hand, the interquartile range, which we've already introduced, only uses quartiles in its definition, and quartiles are resistant, okay? Therefore, the IQR, the interquartile range, is the preferred measure of dispersion for skewed data. And it's really easy to compute. The interquartile range is just Q3 minus Q1. Okay? The interquartile range tells us how spread out the middle 50% of the data are. And so, since it's only taking into account the middle 50%, it's not going to be affected very much by large or small values in the data set. And that makes it ideal for describing the spread in a skewed data set. Now, Excel does not have a built-in IQR function, but we can use Excel to find Q1 and Q3 and then just do the subtraction ourselves, either on a calculator or in our heads, or we could even do the subtraction in Excel, but we'll have to kind of brute force Excel to do it. So here's an example. Suppose a data set have the following quartiles. So Q1 is 48.5, Q2 is 51, and Q3 is 53.5. We're asked to compute the IQR. So the IQR, by definition, is just Q3 minus Q1. In this case, that would be 53.5 minus 48.5. And you might be able to do that subtraction in your head. If not, just use a calculator, right? 53.5, whoops, minus 48.5 is 5. So that's the IQR. Okay, if we were given just a raw data set and asked to calculate the IQR, what I would do is I would use Excel to find the quartiles first, especially since this data set is not already in order. It would be a pain to have to put it in order. So I'm going to let Excel do the heavy lifting there. So let's remind ourselves how to get quartiles, right? So we need Q3 and we need Q1. To do this in Excel, we'll do quartiles dot INC. I want to calculate the quartiles of this data set, and for Q3 that means I want the third quartile. So this is what I'm going to type into Excel. Q1 would be similar, right? Quartiles. Actually, I don't remember if it's quartiles or just quartile, but we'll see when we go over to Excel in a second. We'll see if we need the S or not. And I want the first quartile for Q1. Let's see what we get. This is example 7, so we'll try to find that in Excel. Okay, so we've got example 7 here. Okay, so for the third quartile, I'm going to say equals quartile. Oh, so it doesn't have an S, it's just quartile. That's fine. Quartile of my data set. I want the third quartile. And then for the first quartile, I'll select my data set and then say comma 1 for the first quartile. And there we go. So 77.5 and 52.5. Now I know I'm going to be asked for the interquartile range, so I need to subtract these values. I could do that in my head, or I could do that on my calculator, or here in Excel I can say equals Q3 minus Q1. Okay, so there's my IQR, 25. So I've got 77.5 for Q3, 52.5 for Q1, and then 25 for the IQR. Oh, what was it? 52.5. And so the IQR is Q3 minus Q1. That's 77.5 minus 52.5, which comes out to 25. Oh, wait a second. Yeah, that's right. Okay. All right. So that's that. Now, as far as interpreting the IQR is concerned, it has the same interpretation as the standard deviation. Okay, so it's a measure of dispersion, or in other words, it's a measure of spread, or a measure of variation. The larger the IQR, the more spread out the data. Okay, in other words, the more variety there is in the data set, or you could say the less consistency there is in the data set. Okay, so that's our interquartile range. Let's look at the index of qualitative variation. Okay, so what we've discovered so far is for quantitative symmetric data, we'll measure the dispersion of the data set with the standard deviation. But if the data set is skewed, then the standard deviation is not going to be a good measure of center. So instead, we'll use the interquartile range. This still leaves us with the question, what do we do if the data set is categorical? Okay, well, so what if we have a categorical data set? In that case, we would use, well, there are actually multiple measures of dispersion you could use, but one of them is the index of qualitative variation, and that's what we'll use in this class. Okay, so the index of qualitative variation, or IQV, is a measure of spread for categorical data, and this is the formula for the IQV. Okay, so the IQV, to calculate the IQV, first we'll find the sample proportion of each category. We'll square that, and then we'll add those up. Okay, and then we'll do 1 minus that sum, multiply that by the number of categories k, and then divide by the number of categories k minus 1. So the IQV, let's just talk a little bit about the IQV. The IQV is going to range from 0 to 1. So the smallest the IQV can ever be is 0, and the largest the IQV can ever be is 1. Now, just like with the standard deviation and the IQR, the larger the IQV, the more variation. So an IQV of 0 would indicate no variation at all. All the data is in the same category. And an IQV of 1 would indicate maximal variation. So the data are equally distributed across all possible categories. So this is a good illustration of that, right? So let's say that you were looking at the sales volume on each of the 5 weekdays of the week. If the sales volume is identical on all 5 days of the week, then you would end up with an IQV of 1. Okay? If there were some variation, like if Mondays were slower sales days than Wednesdays were, or something, then you would get a slightly smaller IQV. Okay? The data is still spread out across all 5 days of the week, but it's not equally spread out, and so you get a slightly smaller IQV. Now, if the data were spread out just across the Tuesday, Wednesday, and Thursday, so that Monday and Friday didn't have any data in them, well, then you'd get an even smaller IQV than before, right? And you can see here there's even less variation. Here there's even less variation. And then here, there's no variation at all. All of the sales take place on Wednesday. Okay, so we would get an IQV of 0. So this is how we interpret the IQV. Let's look at another example of that. You ask a random sample of 65 people from each state which snack they prefer at a Super Bowl party: corn dogs, nachos, popcorn, buffalo wings, or pizza. Which state likes a greater variety of snacks at their Super Bowl party? Minnesota with an IQV of 0.7, or Wisconsin with an IQV of 0.65? Our answer would be Minnesota, because they have a larger IQV. So they like a greater variety of snacks. There's more variety in their snack choices. So we would say Minnesota, because they have a larger IQV. Okay, so the same kind of interpretation of the IQV as we had for the standard deviation and for the IQR. But let's practice calculating the IQV. because unfortunately there is not a built-in Excel function to calculate the IQV. So it does take a little bit of work. As always, you can find step-by-step instructions for doing this in the Excel stats procedures. So if you're stuck on a problem or something, just refer back to those. There will be a short video there explaining how to do this as well. So let's practice, okay? This example says, a student walked around her neighborhood and recorded the number and type of each tree she saw. Her observations are recorded below, okay? And we're asked to create a relative frequency bar chart and then compute the mode and the IQV. So we're actually asked to do several different things here. I'm just going to head over to Excel and do the work there, okay? So let's head over to Excel. This is example 9. So these are the different varieties of tree that she saw. Okay, well, if I want a relative frequency bar chart, I'm going to start off by selecting my data, Control Shift down arrow, and then I'm going to insert a pivot table, and I'll insert that pivot table into our existing worksheet right there. And then you know the drill here, right? So we want all the different tree varieties. We want to count them up. Here's our frequency distribution. We want a relative frequency bar chart. So I'm going to change the frequency distribution into a relative frequency distribution by calculating the column percentages. And now to get a bar chart, I would select that and go to Insert, Bar Chart. Okay, so that's that. We were asked to calculate the mode. The mode is pretty easy to see now. It's cypress trees. Those were the most common trees in her neighborhood. You can tell that because it has the largest proportion. So the mode would be cypress, and the modal proportion would be 23.81% or 0.2381. Okay, but what about the IQV? All right, so the IQV. In order to get the IQV, what we need to do is we need to square each of these sample proportions and then add those up, and then we'll plug them into the IQV formula. Okay, so the way that I'm going to get these, the way that I'm going to be able to square these values is, first of all, I'm going to copy this table and then I'll paste it right here, but I don't want to paste the pivot table. I want to paste just the values. Okay. These are actually proportions, so I'll change that label. This is the tree variety. Okay. Let me make this a little bigger so we can see it. Okay. So in this next column, I'm going to create a new column, and I want to square the proportions. And the way I'm going to get Excel to square the proportions is I'm going to click this cell, and I'm going to say equals, and I'm going to say that number, and then I'm going to do caret 2. The caret button is the 6 on your keyboard. So if you hold down Shift and hit 6, you'll get that caret symbol. And this means that we're going to square the cell G3, right, which is the one that I selected. So I'll hit Enter. Okay, and this is this number squared. Now I can do all the rest of them the same way, or I think if I click on this little square at the bottom right corner and drag this down, it'll do those calculations for me. Okay, and you can check up here to make sure that that is indeed the calculation. Oops, that's not what I wanted it to do. But you can check to make sure that it's performing the calculation you want it to. Okay. Yes. Okay. So what I want to do next is I want to add up these values. So to add these up, I'm going to say equals, and then I'm going to use the function sum. Okay. And I'll click on these, close the parentheses, and say enter. So now this is the sum of all of these values. Okay. Let's maybe write down what we've done so far. So we know that the mode is cypress trees. We got the relative frequency bar chart here. And we know that the sum of our squared proportions is about 0.163. Okay. So the mode was cypress. And the IQV is k times 1 minus the sum of our squared proportions divided by k minus 1. And we just used used Excel to get this sum of our squared proportions, right? It was 1 minus, this part was, I forgot, it was about 0.163. So I'll say this was about 0.163. Oh, and I can replace k, of course. For k, we need to know how many different tree varieties there were. So looks like there were 1, 2, 3, 4, 5, 6, 7, 8 different tree varieties. So this would be 8 times 1 minus 0.163 all over 8 minus 1. And now this I can just type into my calculator, or you could do it in Excel, right? Either way, but I'll use a calculator. So I'm going to do 8. Let me give myself a fraction. Okay, 8 times 1 minus 0.163, okay, divided by 8 minus 1. And there we go. So it's about 0.957. Okay, so there's my IQV. So that's how we would compute one of those. Again, the IQV has the same interpretation as our other measures of dispersion. The larger the IQV, the more variation there is in our data set. In our case, we have a fairly large IQV. It's close to 1, which is the maximum value that the IQV can ever get. And I think that corresponds pretty nicely to our data set because there is quite a bit of variety here. Okay, it's not perfect. Some of the varieties are much less common than others, okay? But there is still a good deal of variety here. Okay, so to summarize what we've learned in this section, if you have numerical data that is symmetric, then as we learned a couple sections ago, the measure of center to use would be the mean. What we learned in this section is that the measure of spread to use is going to be the standard deviation. If you have numerical data that's skewed, then as we learned a couple sections ago, the measure of center to use would be the median. And as we learned in this section, the measure of spread to use would be the interquartile range, or IQR. And then finally, if you have a categorical data set, then as we learned a couple sections ago, the best measure of center would be the mode. And as we learned in this section, the best measure of spread would be the index of qualitative variation, or IQV for short. And that's it. That's what we have for measures of dispersion. What I want to do on this last page is just go back to the standard deviation. I said that we would give a derivation of the formula for the standard deviation. So if you're interested, you can continue watching, and if not, that's okay too. You're not going to be tested on this this idea, but I didn't want to just throw out a formula and not give you some justification as to why that's doing what we're claiming that it's doing. So let's go through it, right? We know that the standard deviation is an attempt to measure the average amount by which each observation deviates from the mean. And so this is the formula that we claim does the trick. So let's see why. In order to find the average distance from the mean, which is what we're kind of trying to do, we first need to figure out how far each individual observation is from the mean. And this is called the observation's deviation about the mean. Okay? And we would calculate that by just subtracting it from the mean, subtracting each observation from the mean. Once we have those individual deviations, we can compute their mean, their average. Okay? But there's a slight issue here. So let's note what happens when we compute the mean of the deviations for this very small data set. Okay? In order to compute those individual deviations, we first need to compute the sample mean. So let's do that. X bar would be 1 plus 2 plus 3 plus 4 plus 5 plus 6 divided by 6. And let's see, that would be 3, 6, 10, 15, 21. 21 divided by 6. 21 divided by 6, 3.5. Okay, now we can compute the individual deviations about the mean. Let me just make a little chart for this. So I'll have each observation and then its deviation from the mean. So we have 1, 2, 3, 4, 5, and 6. We would do 1 minus 3.5, that's negative 2.5. 2 minus 3.5 is negative 1.5. 3 minus 3.5 is negative 0.5. 4 minus 3.5 is 0.5. 5 minus 3.5 is 1.5. And 6 minus 3.5 is 2.5. So these are the individual deviations about the mean. But note what happens when we compute the mean of these deviations, right? So if we now try to average these values, we would do negative 2.5 plus negative 1.5 plus negative 0.5 plus 0.5 plus 1.5 plus 2.5 and divide by 6. But you can clearly see that this numerator is going to add up to be 0. Okay, so we would get 0 over 6, which is just 0. Okay. So sad times. In fact, the sum of the deviations about the mean is always going to be 0. And this is bad news because our whole goal was to find a good measure of center that would describe that would be larger the more spread out our data set is. But if we're always getting 0 every time we compute one of these things, then that's not going to be a good measure of center. It's not going to give us any information whatsoever. So what we do to take care of this is we're going to make all of the deviations about the mean positive, so that when we add them up we don't get 0. And the way that we do that with the standard deviation is by squaring the values. Okay, because notice that when you square a negative number, you get a positive number. And when you square a positive number, it stays positive, right? So like negative 2 squared would mean negative 2 times negative 2, which is positive 4. So squaring the values will make all the values positive. Now some of you might be thinking, why don't we just take the absolute values though? And you could do that. That would yield a statistic called the mean absolute deviation, or MAD for short. But we don't do this when we're computing the standard deviation, because squaring the values instead of taking the absolute values, it just is easier to work with algebraically. The standard deviation will show up in the probability distributions that we use to perform inference later on in the semester. And so the standard deviation is just, it's simply more useful for us. So, okay, so we'll make the values positive by squaring them, and then we'll calculate the mean of the squared deviations. And then finally, we'll sort of undo, maybe I should put this in quotes, but we'll sort of undo the squaring by taking the square root at the end. And that's why we get this for the population standard deviation. So let's break that down, right? We're finding the deviations about the mean, we're squaring them, and then we're finding the average of those squared values by adding them up and dividing by the number of values in the data set. Finally, we undo the squaring by taking the square root at the end, and that's how we end up with the formula for the standard deviation. Okay, one last thing to say about the formula. For the sample standard deviation, we divide by n minus 1 instead of by n. And we do that, as we mentioned earlier in the lecture, so as not to underestimate the true population standard deviation. Okay, if we divided by n instead of dividing by n minus 1, the result would be what's called a biased estimator. Okay, in this case it would be a biased estimator of our variance, sigma squared. And what that means is that it's a systematically bad estimate. And it turns out the math just happens to work out so that if you divide by n minus 1 instead of by n, then we correct for that error. And that yields what we call an unbiased estimator of sigma squared. Again, you're not going to be tested on any of this, but if you're interested in some more detail, you could just Google biased estimator, or you could watch this video. So you should be able to click on that link if you're looking at the notes on your computer. So that's all I'm going to say about the derivation of the standard deviation formula. Again, it just didn't feel right to me to just throw that formula at you without some explanation as to where it comes from. So that's that. I'll check in with you again in the next section.